How are y'all doing today?
Doing all right. How are you?
So today is going to be our review session for the exam. And so I'd like to talk a little bit about the exam and the scheduling and all that kind of stuff for tomorrow. And I'm going to need you guys' input on this. So the first thing that I want to say is that the practice exams that I uploaded for you guys to play around with, and I'm happy to answer any questions about those in just a couple of minutes, were 35 questions long. Your exam tomorrow will not be 35 questions long. It will be 25 questions long. So let me explain how things are going to be laid out. There will be 5 theory questions at 3 points each. And these will be similar to problems 1 through 10 of the exams that I've uploaded. So we're talking about definitions that we've gone over in class. So voltage, current, power, energy, nodes, meshes, what it means to be in series, what it means to be in parallel, those kind of things, or simple, Ohm's law relationship, give you, ask you like which equations correctly relate power and energy, things of that nature. Then there will be 20 analysis questions at 4.5 points. So these would be similar to problems 11 through 35 on the previous exams. There might be, like one circuit you might be asked 2 questions about, other circuits you might only be asked 1 question about, etc. But I'll have it split up in such a way that you can easily see which circuit goes with which problem, and all that kind of stuff. The material to be covered on this exam is everything from our first lecture, which June the 7th, up to when source combination and maximum power transfer theorem were covered, which would have been the pre-recorded video lecture that you guys watched on June the 22nd. Okay, so Thevenin and Norton equivalent circuits are not on this exam, but everything other than that is fair game. Are there any questions about the material that I could choose to ask you questions about?
No, sir.
All right, so now let's talk about timing. So typically speaking, I give, when we have in-person exams and all that kind of stuff, I give everybody 90 minutes, or excuse me, not 90 minutes, 2.5 hours, so 150 minutes to do those 35 question exams, because you are going to have to copy down circuits in order to, apply, say, nodal analysis, mesh analysis, etc. You can't really do that with the picture on the computer, or I would be hesitant to do that because I'd be afraid I'd make a mistake. I'm going to give you the exact same amount of time, 2.5 hours, to work those 25 questions in total, okay? I'm giving you this extra time so that you have time to write down or copy down the circuits and apply the analysis techniques. So effectively, I'm giving you this time so that you don't have to freak out and copy stuff down in a hurry and potentially make mistakes that wouldn't be made if you had a paper test in front of you. The exam is absolutely designed to be completed in under 90 minutes, honestly, pretty easily. But I'm giving you effectively an extra hour so that you can slow down and think about stuff, because I don't want to see silly mistakes made from you copying stuff down incorrectly. So let's start there. Does that sound reasonable?
Quite reasonable.
Okay. So I want to be clear, like I've had in the past, students talk to the dean and say that I'm creating tests that are supposed to take 2.5 hours, and it's like, I'm absolutely not trying to make it. I'm trying to wrap things up or whatever. So I am allowing you to take more time so that you can work at a reasonable pace and still copy stuff down. Okay, so just want to be clear. I'm explaining it to you. I feel thoroughly. So if and when you complain to the dean about my test being too long, I can say, actually, it's not. I designed it for this time and allowed the students an extra full hour to write stuff down on their own. Okay, so with regards to the timing, because a large portion of the class is taking this asynchronously, my goal, I'm going to have version 1 will be from 10 a.m. Until, say, 12:30 p.m. Version 2 will be from 1 p.m. to 3:30 p.m. Version 3 will be from 4 p.m. to 6:30 p.m. And version 4 will be from 7 p.m. to 9:30 p.m. Do any of those 2.5 hour windows not work for any of you?
Do we get to choose which one?
Absolutely. So what you will do is you will just pick one of those time slots and then take your test during that time slot, and then you're good. So you don't have to pick. If you want to study more and take your exam tomorrow evening and that works with your schedule, fantastic. I have no problem whatsoever with it. If you'd rather get it done at 10 o'clock in the morning so that you don't have to spend the rest of your day thinking about circuits, that's perfectly fine too. You get to pick one and take it. If you, for whatever crazy reason, decide to take it more than once, I will count your lowest score as your grade. So take it once, or you're wasting your time and mine. So, do any of these 4 available time slots not work with any of your schedules? All right, nobody's saying anything. So I believe that I have covered the point values for the various types of questions. I've talked about why you were getting 2.5 hours to complete the exam, and I have established the 4 2.5 hour time slots with which you can complete your exam. Again, you just get to pick whichever one works best for your schedule for whatever reason you feel it works best. The exams will be different so that somebody who takes the exam at 10 o'clock in the morning cannot help somebody who takes the exam at 7 p.m. Also, and this brings up another thing, I have all of the exams set to where you cannot review or see the questions or anything like that until I unlock it, meaning you will not have any damn clue what your score is until I manually go in and unlock it to allow you to see your score. So after you submit your exam, unless I've set things up wrong, you are supposed to see effectively nothing. You won't know which questions you got right. You won't know which questions you got wrong. You won't know the correct answer for literally anything. You will not have any idea what your score is. That is absolutely on purpose. I will get everyone's grades to them at the same time before class on Thursday. So is that clear? I don't want 5 emails saying, I don't know how I did on the test. You're not supposed to. Homeworks 9 and 10 go with Thevenin and Norton equivalent circuits. So homeworks 1 through 8 are fair game for the exam.
Now, for the exam, are we going to have to scan our work and send it to you?
That would be my preference. So we're doing this with a Respondus lockdown browser and all that kind of good stuff so that I can hopefully, I'll have a video recording of you so that I can see that you're not, looking at stuff like maybe you had an equation sheet taped to your wall or you're not looking around too much and all that kind of stuff. But I would absolutely prefer that you scan your work and send it to me as well. And I'll open up a portal on Moodle to allow you to do that. So if you don't have like an actual scanner at your home, there is an app that you can download for most smartphones called Cam Scanner that will allow you to effectively use your phone as a scanner. And so you can take pictures of multiple pages of your test, save it all as a single PDF and upload that. That'll be another way for me to check things and try to make sure that people with similar scores on the same version of the test weren't, I don't know, somehow trying to cheat. There is no equation sheet for exam 1. That is absolutely correct. You are just supposed to use a pen, a pencil, and your knowledge. That is the hope. Anything more than that, or sorry, you are absolutely allowed to use calculators, but the calculators that are supposed to be used on this test are TI 36X's, TI 30X's, Casio FX115s, Casio FX911s, and I want to say that there's an HP calculator that is allowed as well, but I can't remember what that is off the top of my test. It's just the regular NCEES approved calculator list that you used in all of your 120 classes and all of your other 220 classes. So to be very clear, no equation sheet for this exam because honestly, pretty much everything is covered with KCL, KVL, and Ohm's law, and then applying those. So if you can't remember those 3 things, you're in trouble for this exam. Any other questions about the test in general?
You said we'd be using Respondus. What is that? I haven't used that in any of my classes.
Okay, so Respondus is a web browser. So right now, if you go to our class's Moodle page and you click on the exam 1 link that I have put up, there is a little, it's called a practice test, but I would hesitate to actually call it a test. Or it says practice exam 1. So if you click on that guy, at the bottom, after it tells you, so it should say something like, attempts allowed 3, this quiz opens today at noon and it closes on Wednesday. There's a time limit of 30 seconds. And then below that, if you do not have the Respondus lockdown browser installed, there should be a link that will allow you to download the Respondus lockdown browser. And then it will go through the steps that I'll be making you do tomorrow. So you'll have to like show some form of ID and all that kind of stuff. So Taj says, can you work out your problems on a tablet? So the Respondus lockdown browser, what it does is you have the window with your test open, and that is literally it. It will not allow you to tab out or anything like that. If you try to take a picture of the exam, it won't allow you, but it'll send me an email telling me that you did, so I know that you're trying to cheat for some reason. Effectively, the only thing that you can have up on your screen is the exam. That's it. No other apps. It will ask you to close out programs and stuff like that that could cause potential conflicts. You won't be able to navigate to other web pages or anything like that until you complete your exam. So that means that you will have to use a physical pen and or pencil and piece of paper to do all of the math required for the exam. By all means, try to break Respondus while you're doing this little 30-minute practice thing. So the Respondus lockdown browser requires the use of a webcam because it records you while you take your test, and then I get a link to all of those videos so that if I see anything that looks suspicious with regards to the scores, or it uses AI to flag suspicious behavior as well, I can view that section of the video and say, oh, that person was just sneezing. They weren't doing something weird. Or it certainly does look like that person is accepting a phone call or something like that. Or talking aloud, etc. Any other questions? All right, so Miss Sarah DeMatti asked if we could do a practice nodal analysis or mesh analysis problem for old time's sake. Absolutely. Do you have a particular question in mind, or would you like me to just make one up?
Preferably make one up.
Preferably make one up. All right. Would you like for this, so let's start. Do you want a nodal problem or a mesh problem?
Let's go with mesh.
All right. And do you want this problem to include super meshes?
Why not?
Okay. And do you want this problem to include dependent sources?
Yes, let's complicate things.
All right, so let's make something just really terrifyingly ugly, but one that we want to be able to solve using our calculator, right?
Preferably.
Okay, so let me see how horrifying I can make something. All right, so this is our circuit of interest, and we are going to be employing mesh analysis. So we can obviously see that there are three meshes. So I'm going to call this guy right here mesh current I1. Call this guy right here mesh current I2. And let's call this guy right here mesh current I3. Because I have a current source in my circuit of interest, I am going to have a current relationship, okay? So I can see that there is a current of 4Ix flowing down through this branch right here. How would I relate that to my mesh currents? Anybody?
Be equal to I1 minus I2.
That is absolutely correct. I1 minus I2. Okay. So because that current source is on the interior of the circuit as opposed to the perimeter of the circuit, that means that I am going to have to write a super mesh KVL equation. So I'm going to combine meshes 1 and 2 into one larger super mesh, like so. And now I'm going to apply Kirchhoff's voltage law around that super mesh. So starting at the bottom left-hand corner, I have negative 10 volts plus 5 ohms times I1 plus 10 ohms times I2 plus 2Ix is equal to 0. I'm going to have to write a mesh or KVL equation around mesh 3, so my non-super mesh. So that tells me that negative 2Ix is plus 20 ohms times I3 is equal to 0. And because I have a dependent source, I am also going to have to express my controlling variable, which is Ix, in terms of my mesh currents. How do I do that? Somebody tell me.
Would that be I2 minus I3?
No. So Ix is defined as the current that is flowing from right to left through the 10 ohm resistor. Can you agree with that statement?
Yeah.
All right, so Mr. Abshire says that Ix is equal to negative I2, and that is absolutely correct, okay? So let me explain why. As the current I2 flows around its clockwise path, when it sees the 10 ohm resistor, it is flowing from left to right through the 10 ohm resistor, and it is the only mesh current flowing through the 10 ohm resistor. Because I2 is flowing in the opposite direction of Ix, that's where the negative sign comes from. So with that in mind, we could rewrite our equations here and break things down into a smaller, into less equations that we could then solve. So for instance, I have 4Ix, so that is actually negative 4I2 is equal to I1 minus I2. So that's going to look like 0 is equal to I1, and then I have negative I2 plus 4I2 looks like positive 3I2. So that's equation 1. And I got that from directly substituting, this guy into here. Gosh, all my equations have Ix in it, as it turns out. Then I am going to have, let's see. So I'm going to have 5I1, and then I have 10I2 plus 2Ix, which is the same as saying 10I2 minus 2I2. So that's going to be positive 8I2 is equal to positive 10. That's the second equation. And I know that I3, so let's see, I'm going to have, for my third equation here, I have negative 2Ix, which is negative 2 times negative I2, which is positive 2I2. So I have 2I2 plus 20I3 is equal to 0. 1, 2, 3 equations, 3 different unknown quantities. So then I could have all of those different mesh currents solved for, and then use that to solve for any other quantity in the circuit that I was interested in. So for example, let's say that this problem asked about the power supplied by the current controlled voltage source. All right. Let's go ahead and solve this system real quick and then talk about how we could determine that specific quantity. Solve for I1, I2, and I3. Just let me know what they are. I'm going to do it real quick like here. Anybody got anything different than me, please let me know. There's a very distinct possibility I made a dumb algebraic mistake.
I got the same thing. Me too.
Okay, so with those 3 mesh currents in mind, do you guys have any idea how we might determine the power supplied by the current controlled voltage source? Or do you have any idea what quantities we might need to determine that power? So let's break this down a little bit here. All right. I would argue that to determine the power supplied by our current controlled voltage source, we need to know the voltage drop over our current controlled voltage source and the current flowing into the negative polarity terminal of our current controlled voltage source, because power is the product of voltage and current. So anybody have any problems thus far? I'll take your silence as meaning that you do not have any problems with my power equation. So what is the voltage drop across the current controlled voltage source? Tell me symbolically what it is. Don't worry about numbers just yet. So it is going to be 2ix, which is the exact same as negative 2i2. So let's see, Dylan Gray, Kevin Cobb, and Taj Wills all got it correct. So I'm going to say negative 2 times I2, which came exactly from it being positive 2ix. So everybody on board with that. Now, we need to determine the total current flowing into the negative polarity terminal of that current controlled voltage source. Who can tell me what that is going to be?
Is it I3 minus I2?
That is absolutely correct. And then we would simply substitute in our numbers and get our answer. So let me do just that. I'm going to have negative 2 times y times z minus y, the way my calculator stores things, is going to be 220 over 49 watts, or 4.49 watts. So what I would like to do now is actually work that exact same problem and attempt to get the exact same result using nodal analysis, because I think that this is a good one to use nodal analysis on as well. Anybody have any problems with that? Like you want me to move on to something else, or would a little review of nodal be helpful? How do I determine which analysis method is better? That is a fantastic question. You asked if I have more nodes, is mesh better? So I would argue whichever gives you the simplest set of equations to solve, generally speaking, is the better one. Meaning that if you can solve it with a 2x2 system, I would personally go that way as opposed to solving it with a 3x3 system, because I feel like I would make less mistakes. That being said, if either way works, like you can solve it using your calculator, I would make the argument that for you guys, it's probably whichever one is the most comfortable for you is the one that you're going to make the least amount of mistakes on. So just as a quick aside, if I had tacked on another window pane like so, you couldn't have used mesh analysis to solve this one, because there would be 4 meshes and your calculator literally can't do it. For this particular one, both nodal and mesh are probably going to be equally difficult. So let me try to copy this guy down again real quick. Ten and 5. That's right. Yeah, 2ix. This guy's a 5 ohm. This guy was 4ix, if I'm not mistaken. And here we have a 10 ohm resistor. Here is our current Ix. So we're going to solve this guy using nodal analysis. So the first thing that I would do is I would identify my nodes. So that's 1, 2, 3, and 4. Which node do I want to be my reference node?
The bottom one.
Bottom one, okay? Seems reasonable enough. That's what I would have chosen as well if I were in your position. So that's going to be my reference node. So I'm going to call this guy here VA, this guy VB, and this guy VC. All right. So I have 2 supernodes in this system because I have 2 voltage sources. Anytime I have a voltage source, I have a supernode. All right, so I'm going to circle them in orange. So this is one supernode containing node A in ground. This is another supernode containing node C in ground. So I'm going to write my voltage relationship equations first for my supernodes. So I could see that VA is 10 volts and VC is 2 times IX volts. Does anybody have any questions about where those 2 voltage relationships came from or how I determined them? If any part of it didn't make sense, please let me know.
All clear.
Okay, so now I need to apply Kirchhoff's current law at any nodes or supernodes that do not contain the reference, which for this particular circuit means I'm just going to write a KCL equation at node B, and that's it, because my supernodes contain the reference, and so I do not write a KCL equation for them. So applying Kirchhoff's current law at node B is going to give me VB minus VA over 5 ohms plus 4IX plus VB minus VC over 10 ohms is equal to 0. Now I need to write my relationship that puts my controlling variable, IX, in terms of my nodal voltages. Does anybody know what that equation is going to be? So I need to have IX is equal to something having to do with VA, VB, and or VC.
Would it be VC minus VB over 10?
That is absolutely correct. VC minus VB over 10 ohms. So for this setup, what I would do is I would probably actually leave IX as a variable to be solved for in my calculator, and I would literally just put VA is equal to 10 volts into this equation right here. And so what that is going to give me is, let's see, so for VB, I have 1 over 5 ohms plus 1 over 10 ohms times VB plus negative 1 over 10 ohms times VC plus 4 Ix will be equal to VA, which is 10 divided by 5 is 2 amps. So that's from this guy right here. I have my VC is equal to 2Ix equation, so that's going to be 0 VB plus 1 VC plus negative 2 Ix is equal to 0. That's that guy. And then I have, let's see, negative 1/10 VB plus positive 1/10 VC plus negative 1 Ix is equal to 0. That's that guy rearranged. 3 equations, 3 unknowns. Sorry. VB is equal to something, VC is equal to something, and Ix is equal to something. So let's throw that into our system solvers and see what's what. Did anybody get similar values for VB, VC, and Ix?
I got the same.
Yes, sir.
All right. So now that we're using nodal analysis, how would we find out what the power supplied by that dependent source is? Well, we do the exact same thing, right? It's going to be a little bit trickier here. So the voltage drop over that source is trivial because it is both VC, which we know, and it is twice Ix, which we know. So that's really easy. So let me tuck it in here. So the power by the current controlled voltage source is going to be the voltage drop over the current controlled voltage source times the current flowing into the negative polarity terminal of the current controlled voltage source, which is going to be VC, which we know. So now let's talk about how we're going to get that current that's flowing through the negative polarity terminal. Any thoughts on that? On how we might determine the current flowing through the negative polarity terminal of that twice Ix dependent source? So VC over 20 is part of it. So I'm going to draw a current directed here to the right, and I'm going to draw a current directed here to the left. So I am arguing that the current that is exiting the positive polarity terminal of that dependent source is the same as the current that's entering the negative polarity terminal, right? So this current is the one I'm looking for, is ICCVS, and this current here must also be ICCVS. Everybody on board with me so far?
Yes.
So now if I apply Kirchhoff's current law at this node, I can say that ICCVS is the current flowing to the left, which I know to be Ix, plus the current flowing to the right, which is just VC over 20 ohms. So ICCVS, using Kirchhoff's current law, is just Ix plus VC over 20. And so to me, that is the way my calculator stores variables, that is going to be Y times Z plus Y over 20, which is 220 over 49 watts, which is the exact same answer we got previously using mesh analysis. So there's one reasonably, like I would consider that to be a harder problem on one of my exams that we've worked 2 different ways in just a couple of minutes.
I have 2 questions.
Sure.
So I am slightly confused on how we got the Ix equation, that's VC minus VB over 10. It's just because my math is not rocking today.
Okay, let's talk about that one first. All right. So Ix is the current flowing from the right to the left through the 10 ohm resistor. Do you agree or disagree with that statement?
Agree.
Okay. So we are effectively just using Ohm's law. All right. So we are saying that the voltage drop with the positive polarity, let me draw it in blue up here. Positive polarity on the right, negative polarity on the left. I'm going to call this guy V10. So that voltage drop is just VC minus VB. Then, because we're using Ohm's law, we divide that voltage drop by the resistance, and that gives us our current flowing through the 10 ohm resistor, which we know to be Ix.
Gotcha.
What was your second question?
Sorry, I cut out there. The second question comes from when we're finding the power for the voltage source. I think I understand where we got the voltage from, but just to clarify that it's the VC because it's on the interior and it's not on the exterior of the circuit, or I have no idea, honestly.
Okay, so nope, not a problem at all. So we got that voltage is 2Ix is equal to VC, pretty much the exact same way that we got that voltage V10 as VC minus VB, okay?
Okay.
So this voltage source right here that I'm re-outlining in blue, okay? The dependent source. What is the nodal voltage present at the positive polarity terminal?
It's the VC comes out of the positive side of the voltage source, and because what goes in must come out, it means that that's the one going over it. I'm sorry, that's a terrible explanation.
That is indeed a terrible explanation.
I'm so sorry.
No, not a problem at all. Okay.
It clicked in my brain as soon as I asked the question, and I didn't want to stop you from explaining.
Oh, no. So the positive polarity terminal is associated with node VC, and the negative polarity terminal is associated with the node ground. So 2Ix is equal to VC minus 0, which is exactly what we have here. And so that represents the voltage drop over our current controlled voltage source. So I could have just as easily said, this is twice Ix, and it would literally mean the exact same thing.
Okay. That makes sense. So that's good.
Yeah, it is absolutely good for things to start making sense before you take the test. It's
Just
way better that
helpful.
it makes sense before and instead of after.
Well, it's kind of one reason I wanted to do like a monster circuit, just so that, you know, here's us on the test, we can get through it.
Sure. Any other questions from literally anybody about pretty much anything circuits related? Can we go over current and voltage division? Absolutely. So do you want to go over it conceptually, or do you want to work some problems and see how it applies?
Work some problems because I'm still kind of confused on it.
Okay, let me change my color here. All right. Trying to think of something that I can do. Okay. I think I did this on an old test, but I don't know if it's one of the old tests that I gave you. So let's say that I have 10 amps. And then I have a 5 ohm resistor here. Let's do, this one is 10, this one is 20. Let's bring one out here as well. And let's call this guy 15 ohms. And what I want to know is this voltage drop. Now you may be saying to yourself, Dr. Hartman, why on earth would you use, it's going to be current division, to figure out this voltage drop? And I would argue that it's actually going to be more easy to do than, say, doing mesh analysis or something and then figuring it out. So if I were going to employ current division to solve for this problem, or to solve this problem, what I would be doing is I would be trying to figure out what this current, I'm going to call it IX, is, okay? Because I know that that current IX times the parallel resistance of 10 ohms in parallel with 20 ohms is the voltage that I'm looking for. Does that make sense? So
Yeah.
I'm saying that V is equal to IX times 10 times 20 over 10 plus 20. So solving for IX gets me that voltage pretty easily. So let's talk about how we could use current division to solve for that voltage IX. All right. So IX, is going to be the known amount of current flowing into my resistive network. So that's going to be 10 amps. In my numerator, I have 1 over the resistance of the branch that I'm looking for the current in, right? So that means the branch resistance is 5 ohms plus that 10 in parallel with 20. And I divide this by the reciprocals of the resistance of the branches. So that's 1 over 15 plus 1 over 5 plus 10 times 20 over 10 plus 20. And so let's see what that is. So 45 over 8 amps, which is 5.625 amps. I multiply that by 200 over 30. I get a voltage of 37.5 volts. So that would be an example of current division. Did that actually help at all, or do you want me to do another one that's a little less weird?
A little less weird.
Okay, so let's start with something easier. So let's say that I have a 5 amp source in parallel with a 4 ohm resistor, a 2 ohm resistor, and a 1 ohm resistor. And I want to know the current flowing through the 2 ohm resistor. So this one's a bit more straightforward application of current division, okay? I can say that I2 is equal to 5 amps, the known amount of current flowing into the resistor network where everything is connected in parallel, times 1 over 2 ohms. So that's the reciprocal of the resistance of the branch I'm interested in, divided by the reciprocal of all of the branches. So 1 over 4 plus 1 over 2 plus 1 over 1. And that is going to give me 5 times, let's see. Ten sevenths of an amp. So I'm going to ask you a question now. If I were trying to find this current I4, what is the only thing that would change?
Instead of being 1/2 on the top, it'd be 1/4.
Okay. Now, let's say that I wanted to find this current, let's call it I1, flowing up. What would change?
Wouldn't that be a -1 on top? Since
Exactly
your current's
right.
going up.
Yep. So that's easy current division. You got it. So I did the exact same thing that I did in this problem up here. The only difference was I had a 5 ohm resistor in series with some other resistance. And so I needed to take the whole resistance of the branch into account.
Okay, so you just did that 1 over 5 plus all that on the side. That's just the REQ of that branch, and then 1
Exactly
over that.
Yep.
Okay. Okay, I got it.
All right, now let's mess about with some voltage division. And I'll start with the easy one, and then I'll throw in something harder. So let's say that I have 8 volts. And a 6 ohm resistor and a 10 ohm resistor. And I want this voltage V10. How do I get it? I know that my total voltage drop over those two resistors in series is 8 volts. And so I multiply that by, so in my numerator, it's the resistor I'm interested in, which is the 10 ohm resistor. And in the denominator, it's just the sum of all the resistors in series. So that's 6 plus 10. So that's going to look like 8 times 10 over 16. So let's see, that's 80 over 16 is 5 volts. So if I wanted this voltage V6 with this particular polarity, what change would I have to make to my equation?
You would have a negative 6 ohms on top.
That's it. Yep.
So when you're doing voltage division, it's just like straight the numbers off of the circuit. But when you're doing current division, it's 1 over that number.
Exactly right.
Okay.
So the harder example for voltage division would be something like this. And I think we actually worked pretty much this problem in class, but with different numbers because I don't remember what numbers I used. So let's throw a 10 ohm resistor here, 5 ohm resistor here, and a 3 ohm resistor here. And let's say that I want this voltage V10. How do I do it?
That would be 4 volts times 10 ohms over 3 ohms in parallel with 5 ohms, and that in series with 10.
3 times 5 over 3 plus 5 plus 10. Absolutely correct. So you seem to understand current and voltage division.
Yeah, it makes a lot more sense now, but I can see it.
Okay, cool deal. What's next?
Question, not a problem, but these problems, not trying to hate on your problem making, but they seem kind of baby, and I don't know if they're gonna are problems like of this low of a caliber gonna appear on the test? Because
So
sometimes there'll be baby problems on the test, and I'll think that they're really hard. I just don't know it. Like, you actually thought this was supposed to be easy, but it's really not. If you know what I mean. Some
Yeah,
teachers do that.
let me see what's going on in chat here. So can we go over maximum power transfer? I'll do a question regarding maximum power transfer next. So with regards to the application of current and voltage division explicitly, this guy right here is legitimately a test question that I have asked before. 100%.
Gotcha.
For the voltage division problem, something that I've done on a test before would actually be something like this. So this would be something in line, like here's another thing. I literally never tell you, other than superposition problems, I literally never tell you this is a voltage division problem, or this is a current division problem, or you should use nodal, or you should use mesh, or anything like that. That being said, when I look at this problem, I think you should use voltage division. The reason I say that is because I know that from this node, oh, good gracious, what did I just do? That's not the color I wanted. I apologize. Give me just a second. Why are you being difficult? There we go. I know that the total voltage drop between those two nodes is 8 volts. So I have a known voltage over a resistive network. I can use voltage division. The fact that there's a 5 amp source in there means nothing to me if I am applying voltage division. Does that make sense?
Yes.
So the hesitation there, I'm not a fan of. So let me talk my way through it, right? By definition, voltage is simply the difference in electrical potential between two nodes in a circuit. That's literally a definition that I gave you guys.
Yeah.
So I know, again, that this whole node at the top is at 8 volts potential higher than this whole node at the bottom. Dang it, stop erasing stuff. Stupid computer. So I know that there is an 8 volt drop over that 6 ohm resistor in series with that 5 in parallel with 9.
Got it.
So I can apply voltage division. I will ask a question like this on a test and legitimately ask somebody for the current through the 2 ohm resistor, because I know that if you're paying attention, you can see by inspection, it's just 8 volts over 2 ohms. But if you're not paying attention, you're going to waste 10 minutes setting up nodal analysis or mesh analysis for this problem that you could work using Ohm's law. So a complicated circuit like this, where I'm asking for what I feel to be a easy or sometimes even trivial quantity to solve for, is my way of checking whether or not you're paying attention, or whether you're effectively whether you're paying attention, or whether you've learned mesh analysis and you're gonna use that tool for every problem that you see. So it's kind of like that adage or colloquialism: if the only tool you have is a hammer, everything looks like a nail. Right? That's the mindset that some of you get into with usually mesh analysis. Questions like this are my way of trying to break you of that habit, because you could solve for either that voltage or that current in a couple of seconds, whereas if you did mesh analysis, and you could do this with mesh analysis in such a way as to be able to solve it with your calculator. So right now there's 4 meshes, right? Pretty easy to see that there's going to be 4 meshes. But you could do a source transformation. No, you couldn't. I take that back. I'm sorry. I was thinking that you could do a source transformation on the 8 volt source and the 2 ohm resistor in parallel, but that's not right. You do source transformations on, you can do a source transformation with the 5 amp source and 2 ohm resistor in parallel, converting it into a 10 volt source in series with 2 ohms. And yeah, I mean, there are transformation tools and all this kind of stuff that you could use to be able to easily apply nodal analysis or mesh analysis for this circuit. But those two methods are really overkill if all you're looking for is this particular current or this particular voltage, I guess is what I'm trying to get at. So will I ask a question as easy as this one or this one on the test? Probably not. But these two circuits are effectively buried inside this bigger ugly looking one. You just got to know where to look. All right, so Mr. Irons, I believe, asked me to work a problem involving the maximum power transfer theorem. So let's say that let me come up with a circuit real quick like. Ten, 8, 6. This guy. So I might give you a circuit that looks like this and ask you what value of resistor does RL have to be for it to absorb the maximum amount of power possible, and what is that power? Anybody have any ideas on how we might solve it?
I would assume you could probably do source transformations and at least start there.
Absolutely right. So our ultimate goal in a problem like that is we are looking to make this thing look like one of two circuits, okay? So the first circuit, I'm just going to call this guy VS, RS, here's RL, or IS in parallel with RS in parallel with RL. If we get either of these, we can then apply the maximum power transfer theorem pretty trivially. Okay, so source transformations are absolutely one way to go about reducing this larger circuit into this practical source representation connected to the load resistor, or this practical current source representation. A different way to do this would be using Thevenin and Norton equivalent circuits, but we are not going to do that because that's not going to be on the test. So I have a practical voltage source, the 4 volt source in series with a 10 ohm resistor that I could convert into a practical current source, right? So that would be some current source here in parallel with the 10 ohm resistor. in parallel, sorry, that's with the 8 ohm resistor. Here I would have RL, and then this is my 6 ohm resistor. Here's my current source, that is 4 amps. Like so. So I am saying I'm going from this guy up here to this guy here, that these two networks are electrically equivalent. So my first question for you guys is, should the direction of my current source be, should the arrow be pointing up or should it be pointing down?
It should be up because that's where the positive polarity terminal is on the 4 volts.
Exactly right. So if the positive polarity terminal is on top, the arrow is pointing up. And what should its value be?
It should be 0.4.
Yeah, so 4 volts divided by 10 ohms. So I'm literally just going to leave it as that for now. 4 volts over 10 ohms, which is the same as 0.4 amps. So what could we do now?
Could you combine that 10 ohm resistor and 8 ohm resistor in parallel? To,
Absolutely right. So that'd be 80 over 18. 80 over 18, I think is, let's see, 4.444. I don't want to do that. 80 over 18. 40 over 9. Yeah. So that would be 0.4 amps in parallel with 40 over 9 ohms. Here's that resistor RL. Here is the 6 ohm resistor. Here is the 4 amp source. All right. So now we've gone from here to here. Now what can we do?
could you take that, turns that 4 amps on the right side to a voltage source maybe?
So I would do a source source transformation actually on both of these practical current sources. All right. So I'm going to do it to the one on the left and to the one on the right. So that's going to give me a voltage source in series with that 40 over 9 ohm resistor, in series with that resistor RL. And then I'm going to have another voltage source in series with a resistor. So let's just do the resistor and then the voltage source, like so. So this would be a 6 ohm resistor here, right? The resistor value never, the value of the resistor doesn't change, just its position. So should the positive polarity terminal of the leftmost voltage source be on the top or the bottom?
Top.
All right. What value should the voltage source have?
I got 16 over 9. I think it was like a nasty number, but
Yeah, so 40 over 9 times 0.4. So 16 over 9 volts is good enough for me. For the voltage source on the right, should the positive polarity be on top or bottom?
top, and it should be 24 volts.
All right. So now we can see that the 40 ohm resistor, or the 40 over 9 ohm resistor and the 6 ohm resistor are in series, so we could combine them. And the 16 over 9 volt source and the 24 volt source are also in series. So I would say that we have this situation. Here's RL over here. This is 40 over 9 plus 6, whatever that is. So 94 over 9 ohms, I think. And then this guy over here, God, I don't even want to try to do the math. 16 over 9 minus 24 volts.
Why would it not be 24 minus, like to give you a positive number, would it not be 24 minus 16 over 9? I know it's the same answer, but it's just, it looks better as a positive to me.
So I did it that way because I'm putting my okay. Let me think of the best way to explain it. You're 100% right that you're going to wind up getting the exact same answer either way. It's just going to have a slightly different polarity from the way that we're looking at things, okay? So if I drew a current and I followed it around this clockwise path because I have a single loop circuit, right? That 24 volt source is of the opposite polarity as my 16 over 9 volt source. So that's why I need to do subtraction. I'm going to do 16 over 9 minus 24 because I'm putting my voltage source on the left-hand side. That is literally the only reason. It makes no difference whatsoever to the analysis or the answer for the problem. So for example, what I'm arguing is that if I drew this circuit like this, I'd say that this is 24 minus 16 over 9. But my current is now flowing in the opposite direction. That's the difference in sign there. It's just assuming which way your current is flowing. We don't actually calculate the current at all, so it really doesn't matter which convention we choose. As long as we observe that the voltages are of opposite polarity so that subtraction occurs, we are absolutely going to get the right answer. So with that being said, maximum power transfer occurs when RL is exactly equal to RS. So that would be 40 over 9 plus 6 ohms. Which is 94 over 9 ohms. And maximum power transfer occurs when we have, let's see, Vs squared over 4 RS. So that would be 16/9 minus 24 quantity squared divided by 4 times 94 over 9. over 9. 5,000 over 423 watts, which is the same as 11.820 watts. So something like that is absolutely fair game on your exam.
So what is the purpose of the divide by 4?
Okay. So the division by 4, the purpose is because that's the correct way to do it, but let me explain where it comes from. All right. just as a very quick aside here. So let's say that I have my generic circuit, VS in series with RS in series with RL. Okay. Where this is my voltage drop over my load resistance, so this is VL, and this is my current flowing through my load resistance, which is IL. So I can say that VL is just VS multiplied by RL over RS plus RL using voltage division. Does that seem reasonable?
Yes, sir.
My current IL is VS divided by RS plus RL, just using Ohm's law, right?
Yes, sir.
So the power absorbed by that load resistor, PL, is going to be VL multiplied by IL, or I don't know where that extra little line thing came from, which is going to be VS squared times RL over RS plus RL squared. Right, just multiply those two guys together and that is 100% what you get. Now, maximum power transfer occurs, so P max happens when RL is exactly equal to RS. So that is going to give me VS squared times RS over twice RS squared, which looks like VS squared times RS over 4 RS squared, which is VS squared over 4 RS. So that's where that factor of 4 comes from. For the current source representation, where I have some current IS in parallel with some resistance RS in parallel with some resistance RL, P max, where RL is exactly equal to RS, winds up being 1/4 IS squared times RS. So it doesn't matter whether you're using the practical voltage source representation of the rest of your circuit or the practical current source representation of the rest of your circuit, you're still going to have that factor of 1/4 show up. Any other questions regarding source transformations or maximum power transfer? All right, so in the chat a little while ago, Mr. Kevin Cobb asked if we could review superposition. So, Mr. Cobb, do you want to, I guess my question really is, do you want to review the additivity property? So like, do you want to solve a circuit or do you want to solve a word problem?
I'm just generally confused about superposition.
Okay, so let's talk about superposition as it applies to circuits per se. I'm not going to give you guys a word problem on your test. I have done it in the past, but I know specifically I'm not doing it tomorrow. So So let's say that we have the following circuit. We wanted to solve this guy using superposition, okay? So what I might ask you on the test is, what is the contribution of the 8-volt source to the quantity Vx? Or what is the contribution of the 2-amp source to the quantity Vx? When I ask that question, what I mean is, what value does Vx have if the 8-volt source is the only source that's on? Or what value does the Vx have if the 2-amp source is the only one that's on? So let's work this guy specifically with the voltage source on and the current source off first, all right? So this would be, what is the contribution of the 8-volt source to Vx? That's literally how I would ask the question on the exam. So the 8-volt source is on, so it just stays where it's at. Nothing weird there. Can't turn resistors on or off, they just are. So all of our resistors are going to be where they're currently at. So, Mr. Cobb, do you recall how to turn off a current source?
Wouldn't you just short it so you would have a wire in between the 5 and the 3 ohm resistors?
That is incorrect. Okay, so let me explain why. Yeah, no, perfectly fine. Let me explain why. In a short circuit, so for a piece of wire, which is what a short circuit is, we know that the voltage is 0, but we have no idea what the current is. Current could be anything it needs to be. We are looking for a situation specifically opposite of this. We want the current to be exactly 0 and the voltage to be whatever the heck it needs to be. So that would be an open circuit, right? So this guy, sorry, is how we turn a current source off. And this guy is how we turn a voltage source off, all right? So current sources are turned off by replacing them with open circuits. Voltage sources are turned off by replacing them with short circuits. So the picture that I've drawn on the left is exactly correct for the current source being off. We good for that part?
Yes, sir.
All right, so now, Mr. Cobb, how would you go about solving for that voltage Vx prime?
Just use Ohm's law, right?
Ohm's law wouldn't work, but I argue that voltage division is more efficient.
Okay.
So for Ohm's law, you would say that you have 8 volts divided by the total series resistance and then multiply it by that 8 ohms. Voltage division gets us there without ever solving for the current effectively. So using voltage division, we would say that Vx prime is equal to 8 volts. Our voltage, or excuse me, our resistor of interest is the 8 ohm resistor. Our total series resistance is the 5 ohms plus the 3 ohms plus the 8 ohms. So this is going to give us 4 volts. So it does exactly what you wanted to do, but you took 2 steps and I take 1. Nothing wrong with the way that you chose to do it whatsoever. And it's really not that much more math, but if I have an opportunity to refresh you guys on voltage and current division, I'm usually going to use it. All right, so now we'll analyze the circuit with the voltage source off. And the current source on. And so this would be what is the contribution of the, I don't remember what size it was, 2 amp source to the quantity Vx. So as we discussed a moment ago, to turn the voltage source off, we replace it with a short circuit. So that's that guy. Then we have our 5 ohm resistor. Here we have our 2 amp source. Then we have a 3 ohm resistor. Here we have our 8 ohm resistor, and I'm going to call this guy Vx double prime. So now, how could we go about finding that voltage Vx double prime?
Would that 5 ohm resistor be shorted because it's connected to both sides of the 2 amps?
So it's not shorted out because it's not connected on both sides to the same node.
Okay. Oh, I see.
Would you use current division to solve this one?
You could. So I could use current division, figure out how much current is flowing through that right branch, and then multiply that current times 8 ohms, and that would definitely get me the answer. But I'm going to approach it in a slightly different way. Let me see what the chat's saying. Mr. Abshire is talking about exactly what I would have done. So I'm going to do a source transformation on my practical current source and then do voltage division again because that seems really trivial. So I'm saying that I can convert that 2 amp source in parallel with a 5 ohm resistor to a 10 volt source in series with a 5 ohm resistor, which is then in series with my 3 ohm resistor, which is in series with my 8 ohm resistor. And this guy is Vx double prime. So we could say that Vx double prime is just 10 volts times 8 ohms over 16 ohms is 5 volts. Current division would absolutely work. So current division and Ohm's law would get us there in 2 steps, and source transformation also gets us there in 2 steps. So I just happen to use source transformation. I'll outline how we would do it using using current division as well, just for the sake of argument. So let's call this guy right here Ix double prime, where we could say that Ix double prime is 2 amps times 1 over 3 ohms plus 8 ohms because that's the total resistance of that branch that we're interested in, divided by 1 over 5 ohms plus 1 over 3 ohms plus 8 ohms. And then Vx double prime is just 8 ohms times Ix double prime. And just for the sake of argument, let's do the math here. So 1 over 11, 1/5 plus 1/11, all that multiplied by 2. So 5/8 of an amp, multiply that by 8 ohms gives me 5 volts. Same exact result either way. We could have also done nodal analysis or mesh analysis or anything like that, but I feel like that would have been more complicated than either of these two particular ways. So we figured out what the contribution of the 8-volt source was. We figured out the contribution of the 2-amp source was. So using superposition, what is the voltage Vx in our original circuit, Mr. Cobb?
So to figure that out, would you wouldn't just add your two answers together, would you?
Exactly correct. So it's just going to be Vx prime plus Vx double prime. That is the beauty of superposition. If it's linear, we can just add the results together from our more simply analyzable circuits.
Okay.
Yeah, so that'll let us calculate any voltage or current, but we cannot use it for power. I won't ask you to use it for power, but we absolutely cannot. Because power is not a linear quantity, because it is a product of voltage and current. So it's based on the voltage squared or the current squared, which are nonlinear relationships.
Okay. Thank you.
Yep. So on the exam, literally the only thing different I might do is make the circuit slightly more complicated for you to analyze, but the process is literally identical. You just turn, if I ask for it with, the voltage source on, you just leave that voltage source on, turn off all of the other independent sources, meaning if there are dependent sources there, you have to leave them on all the time. And then go from there. Any other questions? So let me say, I know that class is supposed to end in 7 minutes, but I'm happy to stay on a little late today and answer any more questions if you guys have any. So if you're thinking, I don't want to ask one because we might run long, by all means, ask the question.
Money's all set.
Do you have any advice for how to see the quickest way to analyze these circuits?
Unfortunately, it's just lots and lots of practice. I mean, I can say I do it this way, or I'm choosing to do it this way, and it's because I've been teaching this class for 5 years straight, and I've been analyzing circuits for 10 years before that. So it's just lots and lots of practice is really the only way to get really quick at saying this way is probably the most efficient. And I still make asinine mistakes and overanalyze things every now and then. So largely on the exam for sure, do whatever you feel the most comfortable with. And if you hit a roadblock, then say, all right, how could I approach this differently? I'm trying to give you guys enough time to be able to do that. Homework 4, question 5. All right, let me pull up the web work and we'll take a crack at that one. Homework 4, problem 5. Okay, let me get a new sheet of paper and we'll take a look at this guy. All right, so I'm going to draw it here real quick. And I'll just use the values that I have. So R1 is 41 ohms. R2 is 8 ohms. Ohm resistor here. Take that back. Let me stretch this out a little bit more. So this guy is 100 ohms. R3 is 43 ohms. R4 is 16 ohms. This is 250 ohms. And I'm going to set everything up to where all my currents are positive just because I don't want to deal with a bunch of dumb negative signs. So let's see. I1 is 1 amp. I2 going to be 8 amps flowing this way. And I3 is going to be 2 amps flowing this way. We want to determine, I believe, this quantity I sub x and this quantity V sub x. All right. So in this problem, we are told explicitly to use source and resistor combination techniques to find Vx and Ix. So since there's going to be some resistor combination techniques involved, the first thing that I'm going to do is I'm going to identify my nodes. So this is all one node. This is all one node. Then I've got this node right here. And this node right here. So where'd the chat go? Madison, could you please tell me if there are any resistor combinations that we can make right now?
The 41 and 8 are parallel.
Okay, so the 41 and the 8 are in parallel. You're absolutely correct. So so the 41 and the 8 are in parallel, and they're in parallel between the green node and the red node. So what I'm going to do is I'm going to erase the 41, and I'm going to erase the 8. And I'm just going to put, holy hell, what others to do, sorry. (41) in parallel with 8 between the red and the green. So it's going to be 41 times 8 over 41 plus 8. That doesn't look like times very well. So 41 times 8 over 41 plus 8. So that's those two guys in parallel, right? What else can I do?
Uh, 43 and 16 are
In
parallel.
series with 100.
Okay, so I heard two different things, and absolutely both suggestions are correct. So the first thing I heard was that the 43 and the 16 are in parallel, which is true. So I can put 43 times 16 over 43 plus 16 right in here. And the suggestion was made as well that the 41 times 8 over 41 plus 8 is in series with the 100. So I'm going to go ahead and do the math out and then combine those two guys. So 41 times 8 divided by 41 plus 8 plus 100 gives me 106.694. And I can do the same thing down here, right? So that's going to be 250 plus 43 times 16 over 43 plus 16, which gives me 261. .661. Right. So now I can see that I've reduced my network to where everything is in parallel, right?
Yes.
So what can I do to current sources that are in parallel?
You can add them up.
Okay, so all of the current sources are in the same direction. So that means that I could use an equivalent current source that is just 1 amp plus 8 amps plus 2 amps. So I'm going to say that I have an 11 amp source up here and get rid of these guys. So I'm going to redraw this real quick because that thing is way too dang big. What I have right now is an 11 amp source in parallel with a 106.694 ohm resistor in parallel with a 261.661 ohm resistor. My current IX is the current that's flowing through my 261.661 ohm resistor, and my voltage Vx is positive polarity on the left, negative polarity on the right. So, Madison, how would you go about solving for either of those two quantities?
Before that, I have all in the same direction, 10, -9, and -2 amps. So those would all still be added. I'd just have a negative amp at the top.
Absolutely right.
Okay, I just want to make sure. That's where I got messed up doing homework.
Okay. So on my, if all of them are in the same direction, then you just add them all up together, and if you get a negative, you get a negative. I intentionally set mine up to where all of the currents would be positive, but in my problem statement, one of them is listed as negative, and so I just treated it as positive by changing the direction of the arrow. Anyway. All right, so what do we do now?
Find IX.
Okay, how would we do that?
I want to say Ohm's law, but we don't know what the voltage is that is going through the bottom resistor. So I don't know how we make it work.
Do current division?
So we could use current division to find that current without using, without knowing what that voltage is. That's what current division allows us to do, is to determine the current flowing through resistors whenever we have a known current flowing into a parallel combination, right? So I could say that IX is going to be negative 11 amps times 1 over 261.661 divided by 1 over 106.694 plus 1 over 261.661. So let's figure out what that's going to be. Negative 3.186 amps. And from this, how can we determine Vx? Can we use source transformation for Vx? We could, but we have to be careful here. So could we do source transformation and then voltage division? So 100% we could, but that's not what I'm going to do, okay? What we are trying to find is the voltage drop across these resistors, right? But everything is in parallel. So my question is, why aren't we just using Ohm's law? What I mean by that is Vx is just going to be negative 11 amps times the 106.694 in parallel with the 261.661. Everybody understand why?
Why do we have a negative 11 amps?
Okay, so I could say that this voltage Vx is the voltage drop across the 11 amp source, right? With the current flowing into the positive polarity terminal. Like so. Right? So I'm trying to think. It's weird to look at right now because of the way we've drawn it vertically. So let me draw it horizontally real quick, and this might actually help you see what's going on. So this 11 amps of current is flowing into the negative polarity terminal of our voltage Vx. So that's why there's a negative sign.
Okay, thank you.
It's harder to look at for me when it's drawn vertically like that, but as soon as I flip it on its side, it's really easy for me to see why it's negative. Hopefully it's easy for you too. For the current division guy, why we have negative, let me draw Ix here real quick. So Ix is flowing from the positive polarity terminal to the negative polarity terminal. So when that current splits from current division, we're expecting some of it to branch off and flow down this way, and some more of it to branch off and flow down this way, which is opposite the direction as it's defined. So that is where the negative sign came from using the current division. But if we know what Vx is because we used Ohm's law, we could find Ix as just Vx over 261.661 ohms. And we would see that that current also has to have a negative sign that way. All right, what's next?
This is from that last one. So your Vx would be negative.
That is correct. Vx will have a negative value.
Is there a reason web work would take it positive but not negative?
So using my numbers, it has a negative value. If your numbers were different, like if your current, like you had a negative value for your current, right? When you combine all the currents together?
I had a positive.
This is Madison that's talking, right?
Yes.
Let me log in under you real quick and look at your numbers specifically. Let's see, student progress. For problem 5. All right, so overall, let me think of how I can explain this.
I got it. I see where I went wrong.
Okay. 'Cause I'm looking here and I'm just trying to think about how that sign could have got a little bit wonky. I think it has something to do with the value of your current, because you get your current to be very, very small, right? Let me think about this.
Yeah, I had 0.2817.
Right.
It was small.
Okay. Any other questions?
The practice test on Moodle is just purely for practice, no grade.
So it's not even really for practice. Like the first 2 questions are literally, it says the correct answer is like 95. And so you just click the 95 button. So that practice test is more so for you to get Respondus and all that kind of stuff set up this evening and get a little familiar with it before you go to take the test tomorrow, because you don't want the time it takes for Respondus to get itself set up counting against the amount of time you have available to take your exam. There are legitimately 2 circuits related questions on that 4-question practice test. If you want to have a stab at them, by all means go ahead. But the purpose of that practice thing is for you to get familiar with using Moodle and the Respondus lockdown browser to take this multiple choice test.
Will we have any circuits that are drawn like crazy, like the looped one that we had in one of the sections of homework?
No, so if you look on the practice tests and you go down towards the end, like there's that big, huge, ugly problem for nodal analysis and mesh analysis. So there are going to be some like that, but as far as like the loops and curves, no, because I can't draw them in the program that I use to draw the circuits. So like if you go down to problems 30 through 35, those are problems on what I call big ugly nodal and big ugly mesh. You're absolutely going to have something like that to where you have to identify the correct equations. But as far as like a straight circuit analysis problem goes, it's all going to be window pane looking circuit representation. So like the 2 exams that I've 2 prior exams that I've posted are all the questions were made by me, and that's exactly what my circuits look like, and that's the level of difficulty that you should expect.
Okay.
Any other questions?
When will this recording be posted?
So I have to drive from Ruston to my house in Minden, eat dinner with my wife, and then I will tell her that I need to stay up and finish setting up the 4 different timings of the exams, and I will go ahead and edit this video and upload it tonight as well. I would say 9 p.m. roughly will be when it's available.
Okie doke.
Anything else? Thevenin and Norton is on test 2. That is absolutely correct. Thevenin and Norton is not required at all for exam 1. Taj, you're very welcome. Any other questions? Alrighty, nobody's saying anything, so I'm going to pack things up and head on home. Set up your exams and all that kind of stuff tonight, so I will see and speak to you guys. Hopefully, you won't have to talk to me again until Thursday. If you have to talk to me tomorrow, that means something went horribly wrong.